Okay, this is video number 11. So this will be the final official video for this class. So I may do a video for the LBO calculations as well, because several of you have asked that I do that. I may not do it before the official end of the class, but at some point in May, for sure, I'll make that video and I'll make it available to you guys to watch at your own leisure. So I guess this is a good opportunity to thank you all for your patience with my videos. I can't imagine what it's like to be on the receiving end of these. So thank you for not complaining too much. And I'm not even talking about those with mistakes in them. So even the clean ones, it's got to be quite painful. But anyway, there's only one more. So you're almost out of the woods. And so this is our final chapter. It's called the value of flexibility. And so this is a chapter which is about real options. So what are real options? So if you think back of our capital budgeting chapter, what we did there is we did DCF in the capital budgeting context in the most common way in which it is done, namely we outline one benchmark cash flow scenario and then we calculate the present value of that scenario. But of course, in life, in practice, most long-term investment decisions like this come with a lot of flexibility. So for instance, if you think about our plastic injection plant, what's going to happen over time is we're going to discover whether or not the market is going to support our investment. And it may be that we realize that it was just a bad idea, that either what we are producing is not adequate for this market, or maybe macroeconomic conditions have changed, what have you. The point is, I always have the option to pull the plug on a project if I discover in time that is not working out. So just as another example of this, as you know, right now as a business school, we're in the process of deciding what new degrees to introduce, what master's degrees to introduce and the like. And when we do this, a big part of our conversation is always, what is the exit strategy? What if we discover that the program we just introduced is just not the right program for the market for which it's designed? And again, the way we reassure ourselves is we tell ourselves, well, we're going to review what we're doing in 2 to 3 years. And if it just turned out to not be the right decision, then we'll move those resources elsewhere. And you can imagine, I mean, it's kind of obvious that all long-term investments are like this. In other words, most investment projects have option-like aspects. I have the right but not the obligation to take advantage of the flexibility associated with my investment. For instance, I may want to go bigger. If it's working like gangbusters, I'm just going to expand, which, as we will discuss, happens to be a call option. Maybe I want to upgrade my facility. Maybe the apartment building that I designed for a certain market category, it turns out that if I had gone luxury, it would work much better. So I may choose to upgrade my investment. On the other hand, as I said, I may choose to contract the size of my investment, if not shut it down entirely. It should be obvious to you. I mean, any kind of example of a long-term investment you can think of, that these real options account for a significant part of value. What I am saying here is that most long-term investment projects that we can think about, we would not take them on without some flexibility. And in fact, you can make an economic argument for this. If we are in well-functioning markets, by which I mean markets that are essentially competitive, we know that the true NPVs of project cannot be too far from zero. If it were to, if they were, super high NPV deals out there, what people would do is they would compete for them, they would bid them up, and we would expect in well-functioning markets that most NPVs are around zero, higher than zero, perhaps, but not too far from it. Well, then if you combine that observation, the fact that positive NPVs are going to get competed away, or almost nearly competed away almost always. And you combine that with the fact that all investment, like I said, have all that flexibility. It's got to be that taking into account that flexibility is necessary to put a project over the top, to rightly conclude that a project has positive NPV. So again, absent a proper measurement of that flexibility, if you do not take into account the value of that flexibility in competitive markets, you will find that most projects do not have a non-negative NPV. In passing, by the way, and this is a good time to say this as we're closing this course, there is nothing wrong with an NPV of 0 or an NPV of near 0. Remember that a project having an NPV near or slightly above 0 or at 0 means that it is covering its opportunity cost. In other words, it does mean that we are looking at the best, the highest and best use of the resources that we're investing in this project. So nothing wrong with 0 NPVs. It is not the case that you should expect giant NPVs, positive NPVs before you can make an investment. 0 NPV is good news, but that was just an aside. Okay, good. So what we want to do is take into account of those real options. So there's several ways to do it in principle. One is, well, let me review my benchmark scenario. I'm just going to attach probabilities to the likelihood that I'm going to the event in which I'm going to shut down, the event in which I'm going to upgrade, the event in which I'm going to expand, and we're going to have all those scenarios, and we are going to average them to return to the correct and proper benchmark cash flow forecast. That's not the way we do it. And the reason why we don't do this is because those options are completely different animals from a traditional investment projects. And we feel as a field that we should value them independently using option pricing tools and that are quite different in nature from the traditional DCF approach. Again, the reason you want to look at those options in isolation is a bit of a subtle point. In principle, you could just use DCF also to value options instead of slightly different arguments. But I'm going to leave that for Finance 330, which some of you are taking at the same time as you are in this class, but the rest of you will take at some point. Instead, what we're going to do here is we're going to illustrate the pricing of real options using two simple examples. So the first example is we're going to look at an investment project. So you can imagine that you're a developer, you're going to build something, a plant or what have you, and then at some future date, call it date one, you're going to sell it. And you're going to sell it or you're going to continue the project is another way to put this. And you're going to sell it either for $100 million or $50 million. Okay, so it's a simple project. I'm going to build something. I don't know yet if it's going to be very valuable or not quite as valuable, but I know it's either going to be $100 million or 50 millions at some later date in the purpose in which I developed this project for. And we're going to assume that this particular project, which has continuation value either 100 or 50 at some future date, I'm going to discover that later, that project can be activated in two distinct locations. So two different economies, and the project exists in both economies. And in the first economy, in the first location, I'm going to assume that there is no exit strategy. You are stuck with the project. So that means that you're going to take this gamble, which is going to have value 100 or 50 in its primary purpose, and you're just going to get what you get and not throw a fit. You get either 100 or 50, that's it. There's nothing else you can do about it. So that's in location one. And then in another location, so a completely different place where this project can also be developed, there it's going to come with some flexibility. And specifically, after you discover the value of the project and its primary purpose, you're going to be given the option, that is to say the right, but not the obligation, to scrap the project for $60 million instead of continuing the project in its primary purpose. And you're going to do this, better yet, upon discovering the continuation value. So you're going to learn it's worth 100 or 50 in its primary use, but then you get somebody tells you, you know what, I'll just take this project away from you for 60. Now, obviously, that option to scrap the primary purpose has value. It has value specifically when the project is worth 50, because you get to sell something which is worth 50 in its primary purpose for 60 million. So this is what we call a put option. This is the right, but not the obligation, to sell an asset at the pre-agreed price of $60 million. And obviously, if the market value of that asset is below that $60 million, that put option is going to be valuable. In that case, we're going to say that the put option is in the money. Okay, so that's the setup. And again, just to make things clear, project 2 is just like project 1, except that it comes with an option to scrap. So then, because NPV is additive, the NPV of project 2 is going to be the NPV of project 1 plus the value of the option to scrap. So this is the way we're going to value this. We're going to say project 2 has the same market value as project 1, and then we need to calculate the value of flexibility. Okay, now let's assume that I happen to know that the market value in the first location of the project, so that's the location without flexibility, I happen to know that the market value of that project is 70 million. Why? But maybe I saw a project like that transacted, just recently. Somebody bought that particular project for 70 million. So I happen to know the value of that project without flexibility. And so this is something that you'll be used to if you have taken Finance 330. If you haven't yet, you can start getting used to it now. In order to price options, I need to have an idea of what the risk-free rate is, and I'm going to assume that the risk-free rate here between today and date 1 is going to be 5%. Okay, so what questions may we want to ask here? First, that's the key question in this chapter. What is the value of flexibility? So here I want to know what is the value of the option to scrap. And if I know the value of the option to scrap, knowing the value of project 1, I can calculate the value of project 2. So therefore I get the answer to the other question that you may want to ask, which is what is the value of the project in location 2? Knowing the value of the project in location 1. In other words, knowing the value of the project without flexibility. Okay, good. So it turns out that this is a completely traditional option pricing problem. So we're going to do exactly what you are going to do in Finance 330, or maybe what you have done in Finance 330 already. So we begin. What we're going to do, let me first say it, is we're going to use a replication argument. So I do not know the value of the option, but I'm going to create a portfolio that has exactly the same payoff as the option. And that portfolio, I happen to know its value, and I'm going to invoke the law of one price. I'm going to say two portfolios that have the same payoffs in every possible state of the world have to have the same value, and therefore the value of the option is going to be the cost of my replication portfolio. So that's the idea. So let's begin. So first we begin by describing the project. That's location 1 project, the project without flexibility. Either it's going to give me 50 million or it's going to give me 100 million. Okay, so knowing this, what is the payoff on the option to scrap? So the option to scrap in location 2 is going to give me the option to the right, but not the obligation to sell the project for 60. If the project happens to be worth 50, the value of that option is 10. If the project happens to be worth 100, the value of that option is 0. And this is, by the way, right where you see that we are looking at a put option. You may have done this in Finance 300 already. You most certainly have done it in Finance 330 or will do it in Finance 330. When you see those max operators, you know that you are looking at an option. We have a max operator because options give you the right and not the obligation to exercise a particular action. So that means that I'm not going to do an action that gives me less than 0. So 0 is the lower bound on the value of the option. But when the action has positive value, we say that when exercising the option has positive value, we say that the option is in the money. So here the option is in the money if and only if the project has continuation value 50. Great. So this is the payoff. And I'm trying to price that payoff. And I'm going to do so by creating a portfolio that has exactly the same payoff, but I happen to know the value of that portfolio. So how is it going to work? Well, I'm going to build a portfolio as follows. First, I'm going to invest some quantity. I'm going to call it little a, and we're going to discover soon enough what a is. And I'm going to invest this at the risk-free rate. So maybe I'm going to take $1 million and I'm going to invest this at the risk-free rate. And at the same time, I'm going to buy a fraction X of project one. So this project here without flexibility is traded in location one. So I'm going to buy, say, 20% of that project. Or for that matter, I may sell 20% of that project. So I'm going to take a position against that project. Now, in Finance 330, you're going to talk when you do real options a lot about what it means to short sell a particular asset or project. For financial assets, it's obvious. You just enter into a short selling contract. We've discussed it briefly in this class, but that's something that financial markets allow you to do. For real assets, it's a bit more complicated to take a negative position against projects, but there are ways to do this. For instance, if I happen to be a developer in location one, I have tons of those projects on my portfolio. All I have to do is tell somebody, you know what, I'm going to sell you 20% of the payoff of this particular project. That is selling the project to somebody else. If I happen to already have it in my portfolio, selling it is easy. But what about if you do not have that particular project in your portfolio? Well, then there are ways, even for real assets, real estate assets, you'd be amazed by what financial markets afford us to take negative positions against real projects and to approximate what it is that we're going to do here. So long story short, somebody has to be able to to sell a project, namely the people who own the project. At least those people have to be able to do it. But in life, it's even better. There are people in finance are very creative, and there's all kinds of ways to take negative positions, even against real projects. To say it simply, if you want to short real estate in the United States, you have tons of ways to do it using instruments that are traded in financial markets. Okay, great. So so far we have this option to scrap. We know the payoffs, and I'm telling you that I'm going to build a portfolio which involves investing some amount at the risk-free rate and then buying or selling a fraction of project one. And the game is going to be choosing A and X so that the option to scrap and the replicating portfolio have the same payoff. Okay, so how is that going to work? So my replicating portfolio, the one in which I invest A at the risk-free rate and I buy a fraction X of project number one, is going to have a payoff of A times 1 plus the risk-free rate. That's what I'm going to get, and I'm going to get that no matter what. That's what risk-free means. So I get this whether the project is worth 50 or the project is worth 100. And then I bought a fraction X of the project. So if the project is worth 50 and I own 20% of the project, I'm going to get 50 times 20%. And likewise, in this case, I'm going to get 100 times 20%. Okay, so all I need to do now is a touch of algebra. I need this number to be equal to this number, and I need that number to be equal to that number. In other words, I need the option and the replicating portfolio to do the same, to give me exactly the same thing, whether or not, whether the project pays 50 or the project pays 100. So I'm going to solve. This is just a system of two equations in two unknowns. So I'm going to solve. That's going to give me A, that's going to give me X, and I'm going to choose again A and X so that the replicating portfolio has the same payoff as the option to scrap. And once I know this, I know that the value of the option has to be A plus 70 times X. Why? Because if I invest A at the risk-free rate and I buy fraction X of a project which is worth by assumption 70 in location one, that's the cost of my portfolio. So since I have two portfolios that have the same payoff, they have the same cost. So that has to be the value of the option. So let's look at first the algebra from my webpage. So if we go to my notes and we just write out all that I just said. Over here, I go to section, the option to abandon. Here we go. So you will see a wordy version of everything I just said. You know, project 2 is the same as project 1 plus the value of the option to scrap, etc., etc. What we did graphically on our PowerPoint boils down to this. I need the payoff when the project is worth 100 to be the same as the option value, and I need the payoff when the project is worth 50 to be the same as the option payoff when the project is worth 50. So this is a system of two equations in two unknown. Remember that I know that the risk-free rate is 5% in this case. So this is RF is not an unknown. So how do I solve this? So, I mean, the easiest way to do this probably is to take equation 2 and subtract, to take equation 1 and subtract equation 2 from it. And when I do this, those A times 1 plus RF are going to disappear. On the left-hand side, I'm going to be left with 50x. On the right-hand side, I'm going to be left with minus 10. Again, all I've done is subtracted the second equation from the first equation, and that's going to tell me that x is minus 10 over 50, in other words, minus 1.5. So what you want to do is take a negative position of 20% of the project in location 1. You want to sell 20% of the project in location 1. And then once I know this to be the case, so using the first equation, for instance, so this is going to give me 100 times minus 1.5, which is minus 20. So that's a plus 20 going to the other side. So this is telling me that A is 20 divided by 1 plus 5%. And so in other words, that number here, 20 million divided by 1 plus 5% is about 19.05 million. So my portfolio involves investing 19.05 million at the risk-free asset today and taking a short position of size 20% against the project in location 1. What is the cost of doing this? It is A, which is the $19 million plus 70 million times 20%. And the answer is that the cost of that portfolio is 5.05 million because that portfolio exactly replicates the payoff on the option to scrap. That's also the value of the option to scrap. So now I go back to the fundamental equation and it's telling me that the NPV of project 2 is the market value of project 1, which is 70 million, plus the value of the option to scrap, which is 5 million and change. And therefore project 2 is worth $75 million. And it is worth more than project 1. Why? Because it is more flexible. It comes with an option to scrap. That option to scrap has value $5 million. So the project in location 2 is $5 million more valuable than in location 1. Okay, so you have those notes. You can, knock yourselves out and read them at your leisure. Instead, we're going to illustrate this and we're going to redo exactly what the math is doing here using Excel, just to look at the same problem from a different point of view. So let us first write all our assumptions. So there's the high project payoff. There is the low project payoff. There is the exercise price of the scrapping option. So this is how much I'm going to get if I use my scrapping option. There is the risk-free rate. So this is this guy that we denote RF. And there is the location 1 value. That's the value of the project in location 1. So the high value is 100. The low value is 50. The exercise price, what I get if I scrap, is 60. The risk-free rate is 5%, and the payoff in location 1 is 70. Okay, then I'm going to calculate the option payoff. And we're going to do, let me copy those two here because the option payoff depends on whether the project payoff is high or low. And so let's do this. So whenever I have an option, I get the max of two things. First is exercising the option to scrap. So if I exercise the option to scrap when the project payoff is high, I get 60, but I lose 100. If I kept the project, I would keep 100. And of course, I can either do that or nothing, and nothing has a value of 0. Good. So we already computed this. We know that the option to scrap is worthless when the project is doing well. It's kind of intuitive, obviously. Same thing. What is the value of the option to scrap when the project payoff is low? Well, I can sell the project for 60, but I lose 50 because I no longer have the project, I've scrapped it, and otherwise I can do 0. That in that case, the option is in the money and it has value $10 million. Okay, great. And now all I need is my little replication portfolio. Replication portfolio. So I'm going to have my little x, and I'm going to have my little a. So maybe I'm going to put some words here. This is the fraction of project 1 that I am buying or selling. And we actually did the math already, so we know that x is going to be negative. And this guy here is going to be investment in risk-free asset. Okay, wonderful. So right now I don't know what my replication is going to be. So how about I just invest nothing in the project and I put, hey, let me put $10 million at the risk-free asset. I'm just making up number for now. So what would be the cost of this constructing this portfolio? Well, the cost of constructing this portfolio is I have to pony up $10 million. That's easy. Plus, I have to buy fraction 0 of, I mean, whatever fraction I want of the project. And of course, the project costs 70. So if I buy 20% of the project, if I want to buy 20% of the project, it's going to cost me 70 times 20%. If I want to sell 20% of the project, it's going to give me 70 times 20%. Okay, so that's the cost of the replicating portfolio. So, okay, and now all I have to write is the payoff. And this is going to be, my computer's complaining, Control C, Control, okay, doesn't want, why is it complaining? Okay, high, I'm just gonna write it out, high project payoff, low project payoff. And let me remove this spelling mistake here. Okay, good. So what I'm writing here is what is the payoff on the replication portfolio when the project gives me a high payoff, and what is the payoff on the replication portfolio when the project gives me a low payoff. Okay, so part of this is easy. I invested 10 million at the risk-free rate. This is going to give me my payoff, my risk-free payoff. So it's always going to be A times 1 plus RF. That's what it means to be risk-free. And then I also have my fraction X. And of course, if the project is worth a lot of money, I'm going to get X times 100. Okay, so this is what my replication portfolio is going to pay if the project happens to be valuable at date 1. Okay, and now let me do it again. The low project payoff is going to be, well, the risk-free part is not going to change. Risk-free is risk-free. That part of the payoff is always the same, but now I get fraction X of a project which is worth only 50. Okay, Excellent. So we're doing great. So we have an option payoff. We have a replication portfolio. And remember, the name of the game is what must X and A be so that the payoff in the high case is the same as the payoff on the option, and the payoff in the low case is the same as the payoff on the option. So what I just said here is I just restated those two equations. Those two equations say payoff on the replication portfolio equals payoff on the option when the project is worth a lot, and the same has to be true when the project is worth a little. So this is a system of equations in two unknowns, like I said, but here now we have computers, so I'm not going to do any algebra. I could just use the solver here in a brute force kind of way, but I'm going to try to be a little bit more intelligent than that. I'm going to write the gap between where I am right now and where I want to be. And specifically, I'm going to write the square gap between the payoffs. Okay, what do I mean by this? So I'm going to take the gap between what I get on my replication portfolio and what the option is giving me in the same state, and I'm going to square that. Okay, and then I'm going to do the same for the gap between the replication portfolio payoff and the option payoff when the project is not valuable. Okay, so let's look at this objective function. What I have said, this number here is going to be positive whenever there is a difference between the payoffs of the option and the payoffs of my replication portfolio. So the difference could be in the first state when the project is worth a lot, or when the project is not worth a lot. It does not matter. When this number, this formula here is 0, it means that the two payoffs are exactly the same in both cases. The only way this is going to be 0 is if those two numbers here are equal to those two numbers, which is exactly what I want to replicate my option payoff. Okay. So that's great. So right now, of course, I'm very far from where I want to be, but now I can tell the computer, and I'm going to use my solver for that. You know, I've said many times that in this class, you do not need the solver. I'm going to use it here to make it quick, but you do not need it. You do not need it. Why? Because you can just solve those equations, and we already did it actually, and it was much quicker than what we're doing now. This is a place where a tiny moment of algebra does the trick for you, because this algebra is trivial. So we're going to use here, like I said, the solver, but there is no need. It is just for illustration. Okay, so I want the square gap between the payoffs to be minimized. In fact, I want to set it to 0, but it's quite enough to minimize it because a square has to be positive. So making a square 0 is minimizing the square. And by changing what, I'm going to change X and I'm going to change A. Now we have to be careful here because you see this checkbox, it says make unconstrained variables non-negative. We know, we've already solved the problem, that we need some of those variables to be negative. So we're going to uncheck this so that the computer will not be afraid to go negative. So there we go. And then I'm going to push solve. And I'm going to keep the solver solution, and you can see that the solver solution is exactly what we did when what we got when we were doing algebra. X is -1/5, A is 19.05, the cost of the option is 5.05 million. You can see that here we're not quite where it's not quite equal to 0, but it's close enough. If I wanted to make it really equal to 0, I would just, in fact, why don't I go do this? Let me go to my options, to my formulas. Oh, interesting that the computer stopped. So what I'm going to do, it stopped even though I told the computer to not stop, but it stopped at 100 iterations, I guess. So I have a feeling then that if we do this again, I'm going to try. This is not rehearsed at all, so we know that this is going to fail miserably. So I'm going to use the solver, and I'm going to make B19 minimized. So same. So basically, I'm relaunching it. What I think just happened is it stopped at 100 iterations, even though the high project payoff is not quite what it needs to be. So let me resolve it. There we go. Beautiful. So now it did another 100 iterations, and now this I get here a 0 or something that is very, very close to 0. And in fact, the square gap is very close to 0 as well. Okay, so understand, this is only meant for illustration purposes. The algebra is quite trivial here. And when we work on exam version of this problem here, you will see that, I mean, personally, I find algebra easier to use to solve those problems. I mean, you will see it here. It just takes a moment of algebra. It's really not difficult. But still, it's good to do Excel to illustrate numerically what is going on. Okay, so good. So let us go back and take stock of where we are. So far, we've basically answered the fundamental question that we were interested in, which is what is the value of the option to scrap, and therefore what is the value of location to project. And we're saying that location to project is exactly the same as the project without flexibility, plus the value of the real option to scrap. So good. So now let us do at least mention another example. Oh, actually, I forgot to do something important. Let me go back. And what's important here? So this feels like a lot of very specific and kind of tedious algebra, but it's not. What we have done here is we have written a proof of the binomial option pricing formula. So this is the binomial option pricing formula. Why binomial? It's because there's only two possibilities, high or low, up or down. And so this is why it is binomial. This is something that you can expand on by having more than two states. So basically you would have a tree that branches out, become bigger and bigger, and you can have as many states you want. As a matter of fact, in the limit, you can have a continuum of states. So basically any real number could be the outcome of the project. And when you do this, when you start multiplying the number of states, instead of the binomial option pricing formula, you get the celebrated Black-Scholes formula. So this is just a simple case of the Black-Scholes formula, but proving the binomial option formula like we've done actually is also proving Black-Scholes, because you just take the limiting argument that I just said and you can show mathematically, as you will in Finance 330, that it gives you the Black-Scholes, the famous Black-Scholes formula. Okay, so this is just a lot of finance talk. But we should take a moment sometimes, and here is the perfect occasion, to rejoice in the beauty of some of those finance results. So what is beautiful about the binomial option pricing formula? I mean, a lot, in my opinion, but more specifically, you know what's magical about this? What's magical about this is one piece of information I never, ever gave you is what is the probability that we're going to get a payoff of 50, and what is the probability that we're going to get a payoff of 100? Never said anything about that. Never, ever. All I said is it's either going to be 50 and 100. That's it. And yet we were able to price the option without any information about the underlying probability distribution. This is so beautiful and so amazing that the people who actually first wrote this here in 1978 in a very famous paper in finance, they had a hard time for a moment convincing the world that this could be true. How possibly can you price this option even though you have no idea about the underlying probability? And the answer and the sheer beauty of the binomial option pricing formula is that the probabilities are there implicitly. In fact, you can back out from the math that we've done exactly the implied probabilities of whether you're going to get 50 or 100. So that still sounds like witchcraft. I mean, either they are there or they are not. What does it mean for them to be there implicitly? Where they are, fundamentally, is in this number here, 70. 70 is, by assumption, the market value of this project. Well, if the market value of this project is 70, it means that the market has made a forecast as to how likely it is that I'm going to get 50 or 100. So implicitly, this 70 embeds must embed at least one piece of information about this probability distribution. But the two probabilities have to sum up to 1. Correct? This and this have to sum up to 1. So if I have one piece of information, I should be able to back out the one number. This is one equation in one unknown is another quick way to say this. So again, all I'm doing here is not trying to confuse you. I just want to show you that this kind of math, finance 330 kind of math is truly and joyfully beautiful. I mean, this kind of stuff is remarkable. The people who came up with this in the 70s are true geniuses. These are truly remarkable achievements. And like I said, in addition, from this binomial option math, you can just take it to the limit, have more branches, more states in your tree, and you get Black-Scholes for free, which is much easier than the kind of stochastic calculus kind of ways of proving Black-Scholes, at least in my opinion. Okay, so this was a moment of advertising for finance and 330 in particular, and now I will calm down and go back to my second example, which is the option to delay refinancing. We're not going to do the details, the same details here, even though we could. When I teach this course in the fall, I save this part of the presentation for Thanksgiving, the one class that I normally do during Thanksgiving week. I make it optional, but here I'll just talk about it briefly. You will not be tested on this particular part. Everything we've done up to now, yes, you will be tested on the final. But this part here about the option to delay refi, you will not. So you can relax. So what real option or what option are we talking about here? So if you remember the very first program we did in this class, which is the refinancing program from chapter 1, a corporation has the option to prepay a bond, and we did the standard calculation, and we decided that this had a positive NPV value. But this calculation overlooked one option that we have when we refi, which is instead of refinancing now, I can wait a little bit to discover what interest rates are going to be tomorrow. And in particular, it is possible that interest rates will have fallen a little bit further. So for instance, we could imagine that tomorrow rates will be either 8.5% or 9.5%. So of course, if you wait, and given that rates today are at 9%, if you wait, you're happy if they go down to 8.5%, and you're disappointed if they go down to 9.5%. But the basic question is, should the company wait to refinance? Should it gamble on this possibility that rates are going to go down? Well, so the first thing to observe is that if you exercise the option to refi today, you kill the option to exercise a little bit later, tomorrow. Why? Because it costs you $2 million to refinance. So you may refinance to go from 10% to 9%, but if interest rates fall a little bit more, say from 9% to 8.5%, you're not going to pay another $2 million to do this. So exercising the option kills the option to exercise it tomorrow. And we couldn't verify this numerically here with those numbers, but it happens to be true. So that means that refi has a cost, and that's an opportunity cost. So when we calculate the NPV of refi, a cost that we have yet to figure is the value of the option that we have just killed. So we need to measure the value of that option, add it to our cost, and we should measure NPV taking into account the fact that we have killed that option. Okay, now, if you do the math for this, and the math is right here in the final section of the notes that I made available to you, it's exactly the same as the one we just did today in this video. It's just a little bit more complicated, but if you remember how we calculated the value of refi, we say the value of refi is always the present value of the old bond at the new rate minus the principal that I have to retire plus the cost of refi. So this is an option. This is a call option. I get to buy something, namely the old bond, at its current market value. And the exercise price of doing so is having to pay back the principal and the cost of refi. So this is a cost option. And in fact, this is a call option, I'm sorry. And in fact, the value of waiting is going to have, as you will see when you read my notes carefully, is going to have the same max operator. Tomorrow, if I wait until tomorrow, I'm going to exercise if and only if at that point refinancing has is a positive NPV operation. And if I don't, I just do nothing. I have the right, but not the obligation to refi tomorrow if I wait. So good, so I have the payoffs, the two payoffs on the options, and then I'm going to build the replication portfolio. What is the replication portfolio going to be? Just like we did before, I'm going to put some money invested at the risk-free rate, and then I'm going to invest in the underlying asset. What is the underlying asset? Is the bond. I'm going to buy or sell a fraction of the bond, and X is going to be the fraction of the bond that I am buying or selling today. And of course, the cost of doing that is whatever I invest at the risk-free rate plus the fraction times the current market value of the bond. And then we do the same algebra. We can solve for it just like we did before, etc., etc. And that's going to give us that the value of the call option happens to be 777 million. The upshot, the key about that value is if you do the math, and here I'm going to move to the Excel for it. So this is the Excel, which I'm going to share with you, obviously, like I always do. And if you do the traditional refi calculations, those we did in chapter 1, we find that the NPV of refi is positive at 354, but we just computed, or you can go through the computation, we just said anyway, that the value of the option is 777. And the conclusion here is that you should not, even though without before option considerations, the NPV of refi is positive, once you take into account the cost, the value of the option to delay, which you just killed, you should not do it. And here, and now I'm going into some deep stuff from Finance 330, you will find that this will always happen. Once you take into account the value of the option to delay, you actually want to wait. You always want to wait. So why is that? The reason for this comes from something we call the early exercise theorem in Finance 330. And so what does that theorem say? It says that you should not exercise an American option early. It doesn't make any sense to exercise an American call option early. So what is an American option? It is an option that you have the right but not the obligation to exercise at any point before the expiration date. So that refinancing is an example of an American call option, because I can exercise today, I can exercise tomorrow, all the way until the bond goes away. So I can do it whenever I want. So all we just verified here is that the early exercise theorem is true for American call options. However, when you do 330, or if you remember your 330, the early exercise theorem only holds for assets that do not pay dividends. When they pay dividends, then actually it may make sense to exercise the option, and you will do so just before a dividend is coming. Well, the same is true here. The equivalent of the dividend, and I don't have time to get into details here, but the equivalent of the dividend is the fact that we owe interest on this bond. So what we are saying here is not that it never makes sense to refi a bond. Obviously, it must make sense to refi a bond sometimes, but it does not make sense to do it in between bond payments. If you're going to exercise, you want to exercise just before a bond payment is due. And that's what those numbers here are telling us, among other things. But this is not Finance 330. All I wanted to do here is illustrate our option pricing ideas in a quite a different context. So that's it. I'm going to stop here. I will repeat that in terms of being ready for my exam, you are only responsible for understanding example number 1 here. I will not test you on the option to delay refinancing. I encourage you to read my notes, but the only parts that will appear, and they will appear on my final exam, are calculations having to do with the option to scrap. Okay, very good. And with that, we are done with videos for this class, and I will next see you in my office hours.